I will do that, but let me contact our friends at Stockholm and see if they're... Stockholm, are you there?
Yes, can you hear us?
Yes, we can hear you. You're not very loud, so feel free to speak up. We're talking about homework number 6, and we've had many fascinating questions, some of which I've attempted to answer with helpful words. And I think the major difficulty that has challenged the people here in Durham is how to compute the virtual work expression. So I'm about to say more about that. But before I do that, Stockholm, if you have some specific questions you would like answered about homework number 6, now would be a good time for you to ask those questions.
We have no questions.
They're okay. Okay. Today is the 25th. Thank you. Okay. So, let me give the big picture, and then I'll have one more time, and then we'll talk about virtual work in particular. The big picture is the following. We're going to assume that alpha is a function of y and t, and that we will, not t, because we're doing static, sorry about that, a function of y. When we do Fourier analysis, we'll let it depend on time as well. And so it's going to be some coefficients a sub I, which are not functions of time, but are at the beginning unknown, times some functions of y, where we choose these functions of y as equal to sine 2n minus 1 over 2 pi y upon l, right? And what we want to do, I equals 1 up to however many terms we have, 17. We want to determine equations for that, those a sub I. We have several alternatives. How do we construct equations? Well, now that we're this far along the course, I'm going to take the perspective of the dynamicist of which, and from the standpoint of the dynamicist, stack is just a special case, right? So that means I could use Hamilton's principle. And Hamilton's principle would say the following: the integral from T1 to T2 of the virtual change in kinetic energy minus the virtual change in potential energy plus the virtual work dt equals 0. Okay? But in statics, there's no delta t, right? So we can forget about delta t. And since none of these other things are allowed to change in a static formulation with time, this integral from T1 to T2 just gives me that time interval, but that's just a constant, and therefore this reduces to minus del U plus del W equals 0 for statics. And this is known as the principle of virtual work, right? So another thing you could do is just start with the principle of virtual work. Okay, but since we are expanding alpha in terms of the series, and we've chosen these functions, all we really need to do is construct equations for these a sub I. And to do that, we can use Lagrange's equations, which are derivable from Hamilton's principle once we take a solution of this form. So Lagrange's equations, in this case, would be if L is T minus U, this is Lagrange. Lagrange and never to be confused with this. Then Lagrange's equation is just d dt of partial L with respect to AI dot minus partial L with respect to AI equals Q sub I, right? But for statics, again, T goes away, right? And also d dt goes away because nothing's changing in time. So all we have left are these two terms. And so this becomes partial U with respect to A sub I equals Q sub I. Okay, so that's the static form of Lagrange's equation. And someone said that was, I said that. I was trying to give my compatriots in Italy all the credit they deserve. This is sometimes called Castiglione's theorem and is usually taught in sophomore, junior year in a course on statics. It's too long ago, right? Yeah, it's too long ago. Okay. All right. So now, the question is how do we express, thank you, how do we express U in terms of the A's, right? If we're going to use this formula, for example. And how do we express Q in terms of the A's? Okay. Are you still with me? All right. No one has gotten lost yet. All right. So let's look at U briefly, and then we'll do the Q's. U is 1/2 the integral from 0 to L of Gj d alpha dy squared dy. And I'm going to write out y now in longhand for two modes. It's A1 times phi1 plus A2 times phi2 plus other things. Now, if I were really doing this and getting a high salary for doing that, I would write this in summation notation. So if they're going to pay me that much money, they expect me to do that. But the first time you do it, you might want to write out. So we'll put that in here, and we'll get what? We'll have U equals 1/2 the integral from 0 to L of Gj A1 times d phi1 dy plus A2 times d phi2 dy. I'm just differentiating this using this expression. Squared, right? dy. Okay? Are you with? Okay. And now I'm going to write this the following way. It's 1/2 A1 squared times integral from 0 to L of Gj d phi1 dy squared. That's this term squared, right? Plus 1/2 A2 squared integral from 0 to L of d phi2 dy. So that's Gj, right? And that's also squared. That's this term squared. But then there's a cross term, right? Plus 1/2 2 A1 times A2 times integral from 0 to L of Gj d phi1 dy d phi2 dy. Okay? And these are just coefficients. If you tell me what Gj is, you told me what these mode shapes are, these are just numbers. So now this is a quadratic form in A1 and A2. Right? These are all quadratic terms, including a cross term. It will turn out, I think, for your homework problem, if Gj is a constant, this interval turns out to be 0. That's not the general case. I think that's true. When you do the case when Gj is not a constant, but varies with y, this term will not be 0. Okay. Now, what do I need in Lagrange's equation? The static form. All I need is du dA1 and du dA2. I'll do 1. I'm sure you can do that. Okay, let's compute du dA1. Du dA1 is equal to what? Yeah. Yeah, it's equal to what?
It's just a third.
Yeah. So it's 1/2 times 2a1 times this integral, gj dp1 dy1 squared dy1, right? But there's another term that involves a1, plus, notice how cleverly the 2 and the 1/2 cancel, plus a2, the integral from 0 to L of gj dp1 dy dp2 dy d1. And so in the equation for I equals 1, in general there will be two terms, one of which will involve a1 and one of which will involve a2, except for the special case of gj constant and the artfully chosen bug shapes I gave you. This term probably is 0. I think I'm almost certain it is, but you can check it, right? Okay. So that's that part. Now we need to compute. Remember what the Lagrange equations are? This partial u with respect to a1 equals q1, and partial u with respect to a2 equals q2. So I need to compute q1 and q2, which is usually the harder part for most people. Not impossible. It's just for most people that's not. Okay, that's what that's why aerodynamicists get paid more than structural engineers. Yeah, in judgment. Okay. All right. Are you ready to move on with that? Okay. Question about this overall. Okay. Sophomore, do you have any questions so far?
Hello?
Great. Let's move right along.
Do you hear me?
Yeah, I hear you beautifully.
Okay. So it is actually.
Yes.
Yeah.
What's your question?
It is actually needed to solve the integral, or we can do like in homework 5 that we just cancel the integral.
Well, you have to perform the integral. You probably can do it analytically. You don't have to do it numerically. In this case, in a real problem where you have a more complicated physical system, you would probably do those integrals on a computer. Is that your question, how to do the integral?
Yeah. Okay.
Yeah. In your case, I think you should be able to do these integrals analytically. Although when gj is not a constant, but gj varies with y, you can probably do that integral analytically too, because it's a fairly simple variation with y. But you might want to just write a little computer code to do the integral using Simpson's rule, or the trapezoidal rule, or whatever numerical integration technique you like. In fact, if you use MATLAB, you can probably just give it the integral and say, come to do the integral. Yeah. Does that help?
Yeah.
Okay, thank you. All right, now we're going to, what's del W? Well, del W, by definition, is Q1 del A1 plus Q2 times del A2. This really defines Q1 and Q2. So, to find those things, then, I need separately to write down another expression for del W. And I start with physical reasoning. In this particular case, I mean, this is true forevermore for all of eternity, according to Lagrange. But for any particular case, I need to be able to write down the virtual work expression for my system. And for my system, it's the moment about the elastic axis plus times del alpha dy from 0 to L. Okay? And now, what we call the alpha is this summation over, well, I said I wouldn't use summation, so I won't. It's A1 times P1 plus A2 times P2. So del alpha is del A1 times P1 plus del A2 times P2. Okay? All right. Still with me? All right. So we're going to put this in here, and we're going to have del W equals the integral from 0 to L of m sub y del A1 times P1 plus del A2 times P2 dy. And now, having done this before and recognizing I want this form, I'm going to rearrange this. This is del A1 times integral from 0 to L of m sub y phi1 dy plus del A2 times integral from 0 to L of m sub y phi2 dy, right? And I look at this expression and this expression, and I say, aha, or eureka, or whatever. This integral is Q1. This integral is Q2. But now you're not quite done yet, because m sub y depends on alpha. Now I'm not going to do all of this, because otherwise I would have done homework for you. But m sub y is equal to, what do we say? It's MAC plus LE, and this MAC is MAC naught, the constant part, which I allowed you to throw away, plus QC squared CMAC d delta, right? Plus L times E. But, and here's the point, L itself is QC DCL d alpha times alpha plus DCL d delta times delta, right? And alpha is what? Alpha is A1 P1 plus A2 P2, right? So now I've got to take this, put it in here, and put it in these intervals, and do those integrals. But then ultimately what I'll have a virtual work expression which will be something times del A1 and something times del A2. But in these expressions, A1 and A2 will appear along with some other stuff. Is that enough to get you going? Good. Okay. Now, let's make sure that's true of all your colleagues. Right? And is this enough to get you going? Get you moving in the right direction? Okay. Now, again, I think the good news will be, well, first of all, I would do one mode first. And then I might do two modes. And if you're feeling really brave and think you've mastered summation notation, you can do it then. But you're going to end up with a set of linear algebraic equations for A1, A2, and all the rest. Okay? And the number of equations will be equal to the number of terms you retain in the series for alpha. Okay? And in general, those equations will be coupled. That is, in the equation for the A1 equations, well, A2 and A3 and A4 will appear. For the special case where GJ is a constant, I think the equations may prove to be uncoupled. They certainly won't be uncoupled when GJ is not a constant. All right. I can't wait to see the results. I know they're going to be fantastic. Stockholm, are you comfortable working on the Hilbert problem now? Hello? Ask a question about what you're going to say. Either that or you're going to end up with are, let's say, I'll call it the A1 equation. What do I mean by the A1 equation? Just the one that comes from du dA1 equals capital Q1, right? And capital Q1 by definition is the coefficient of del A1 that appears in the virtual vertex. Okay. In general, that equation will be some coefficient times A1 plus some other coefficient times A2 equals 0. Okay? But it may be, or no, it won't be 0. Sorry about that. Because we're doing reversal. There'll be some coefficient times del. Right? Okay. And then the A2 equation, will be some other coefficient times A1 plus some other coefficient times A2 plus equals some other coefficient times del. Okay. And so you can write these, like matrices, you can write this as a 2 by 2 matrix times A1, A2 equals del times some set of coefficients, right? And then you can convert it 2 by 2, you can find A1, A2, and away you go. If you only have one equation, you only have one A, then the opposite. And if you have 3 equations, you would have a 3 by 3 matrix and so forth.
When we do the case when Gj is not constant, we will have the dynamic pressure that is inside the K matrix plus the term for work.
That's
How
right.
do we get that out for solving that for because we can solve for the A event, but that A event are dependent on the
Well, okay. The answer is you're probably not going to get the dynamic pressure outside. So there's going to be some numerics. So once you have these equations, let's talk about what happens once you have these equations. Once you have these equations, you're going to have A1 and A2 proportional to delta, right? You agree with that? Yes. Okay. Then you're going to have L. This is lift, not the Lagrange. The lift is going to be Q, C, DCL, D alpha times alpha, plus DCL, D delta times delta, right? But from this, solving for A's, you know that the A's are proportional to delta. So this whole thing is going to be something proportional to delta. Now this something depends on y, right? At this stage. So now you're going to have to integrate this with respect to y. Okay? And then you'll have what I'll call the total lift. Is this. And this also going to be proportional to delta. And buried in here is going to be the dynamic pressure, right?
How do we get the dynamic pressure out?
I'm not sure you can, but it's not to worry if you can. If you can, that would make your algebra simpler. But if you can't, think about what you're going to do. You're going to have this expression. This expression you can write this expression in terms of A1 and A2, right? Yeah. See that? Yeah. Right. And you're going to determine A1 and A2 from here, right? Okay. Then, for each value of Q, here, you'll have a different A1 and A2. Okay? And then what you're going to do is you're going to choose the Q, you're going to determine A1 and A2, and you know this in terms of A1 and A2. And so now you can make a plot. You can plot lift total versus Q. I will tell you as a hint that it will start out at 0. Right? If Q is 0, there's no lift. You agree with that? And then it will go, I think it will actually go up. But at some point, it will go negative. And that point, that Q, is where I have reversal. Right? So there is some numerics involved. I think these intervals, a lot of these intervals, if you work hard, you can probably do the intervals analytically. But if you have more than one mode, you're probably not going to. If you have one mode, I think you can separate out Q. If you have 2 modes, you may not be able to. And since I haven't done the homework problem yet, I don't know whether you can or not. I suspect you cannot. And I'm almost certain if you have 17 modes, you could. But you can certainly do what I just suggested. Right? So one lesson learned from his homework is you can't always solve things analytically. Sometimes you have to do some numerics. Does that answer your question? Yeah. Okay. Any other questions about that? Hearing none. And recognizing that you have not yet completed this homework, I'm not going to personally assign the next one. But I have to give you a review. Number 7? Yeah. Well, I know you have it, but I haven't asked you to actually work on it yet, right? Are you working on 7 already? No. I was going to be impressed if you work on 7. Okay. But 7 involves flutter, right? I think that's right. And that involves dynamics. But the other great topic of dynamics in aeroelasticity is gust response, or inlet distortion for those of you who do turbine machines. So what I'd like to do in the time available today is talk a little bit about gust analysis. And in the book, there are a couple of things that are done which I'm not going to do unless you absolutely insist on that question. One is I start out with simple sinusoidal motion and then build up to Fourier transforms. I'm going to assume that you can read that and understand it, and I'm just going to start out with Fourier transforms. Okay. Secondly, in the book, the gust example that they do explicitly is for the typical section model of strain. I know this is a hard-working class that wants to do things that are challenging, so we're going to do the wing. It's simple. Although once you see how we do the simple wing, I think you'll feel fairly well convinced that we can do more complicated, using the same methods. That doesn't mean that the algorithm will be more complicated, or the computer code might be a little more elaborate, but we can do it using methods. Okay, I just happen to have with me some notes on gust response. So let's do that. See, that's pages 1 to 4. We're still on 225, right? So I can easily do this. I'll just make this page 5. I could write this again, but I don't think I'll do it. But so let me go through this. About the danger of having the notes pre-prepared is I'll go too fast. So you need to slow me down, right? So what we're going to do is we're going to do a simple gust response analysis. And what we're thinking of is a wing like this with an elastic axis. And whereas in reversal we concentrated on rotation, it turns out that for gust response, the main response of blue airplane is usually in bending. And so often people just include the first bending mode of the wing. So we're going to do one bending mode of the wing. Okay? There's dynamics, so we have kinetic energy as well as potential energy as well as virtual work. So in this example, H of Y and T is the bending of this elastic axis. And this is the kinetic energy of this wing if it's just undergoing simple bending. This is the potential energy where EI is now the bending stiffness as opposed to GJ, which is the torsion stiffness. But notice sort of the same form, it's a quadratic form. But now involves a secondary respect to Y because it's bending of a beam or the twisting of a line. And the visual work is now no longer the moment times delta alpha, right? Now it's the lift times delta H because force acting through a distance gives me work. And there's a minus sign because these aerodynamicists insist on defining the lift as positive up and the displacement as positive down. Only an aerodynamicist can do that. Structural engineer would never do that. But that's why aerodynamicists do it. And they're in charge, at least as far as lift is concerned. And the lift is given by Q times C times dCl the outlet. But the effective, this is really no longer a twist per se. We're thinking of an effective angle of attack as the velocity of the wing divided by the free stream velocity plus the velocity of the gust, because we're doing gust analysis, divided by the free stream velocity. So we're thinking of, if I look edge on to this wing, here's the edge. I'm thinking of this thing is moving up and down with H dot. But it's also flying through a gust field where the gust has a component in this direction, WG. Right? And the gust also has components of gust in this direction. But that's so small compared to U, we neglect it. Whereas this isn't small compared to what was otherwise there, because before the gust, there was no component in this direction. It's this component of the gust that gives rise to an effective angle of attack and causes lift to be produced on this wing. Okay? So that's the basic model. Now, it's just a matter of doing a little mathematics. Using Lagrange Equations, or Hamilton's principle, or whatever we want to do. Okay? But we have to do dynamics now. So we have to include kinetic energy, and we have to allow for the fact that the lift varies from things which depend on time. So this lift is changing with time, but this H is changing with time, and certainly the gust in general. Gust velocity is changing with time. So everything's changing. Okay. Okay. Now, where do we go from here? Well, we can go several places. One thing is we can write this equation down. Where does this equation come from? It comes from using all of this and applying Hamilton. That's where it comes from. And in your homework number 7, you're going to show that. That's why I'm not going to do it today. You're going to do that. In fact, in the homework number 7, you're going to include not only this equation for H, but you're going to include the dynamic equation for alpha as well. You're going to go bending of the swing and torsion. Because I need both bending and torsion in general to do Fourier analysis. In gust response analysis, I can often physically ignore torsion and still get a decent answer. And obviously it simplifies the model. Okay. Next thing I'm going to do is I'm going to use Rayleigh widths or something like Rayleigh widths. I'm going to assume H, which depends on T and Y, is some function of T which I don't know but hope to find, times some function of Y which I'm going to choose. A simple assumption would be that this is equal to Y over L squared. Why would that be a good choice? Well, I know that H should be 0 and Y equals 0, which this certainly is. I also know that, as you'll discover when you use Hamilton's principle, which gives you the boundary condition, you'll discover that dH dy and Y equals 0. It's also 0 if this is clamped, so that not only can the root not translate, it can't rotate locally. Right? So the slope of H, as well as H itself, both of those are 0 and Y equals 0. And that's true, right?
You can't rotate locally?
Mm-hmm. That means if I clamp this, it can bend. It's bending. I'm not doing this right now. But if how am I doing? Sorry about that, Stockholm. You can't see this. Well, maybe. No. But your friends here in Durham are going to tell you that it's okay. You're spinning under gravity, right? But I'm clamping it, so there's 0 slope here, right? If I clamp it all along this edge, not only is there no deflection, there's no slope. The slope is 0 as well as deflection. Okay? Okay. All right. So that's why I choose this function. Now, there are much more complicated functions involving sines, cosines, tangents, and coshs, and those are the natural modes of a clamped beam. And you could use those, and probably if you're doing this for the Boeing company or Airbus, you could use those modes. I take this as an example so you have an idea of what these modes might look like. And by the way, look at this. It sort of looks like a parabola, doesn't it? It's sort of like y squared, right? It's pretty close to y squared.
Why don't you use the sinus of the
because if you're talking about alpha mode,
okay.
well, suppose modes had zero. I mean, I could try to use those modes, but remember what they were. Phi sub n or phi sub I. Plus 1 sine 2n minus 1 over 2 pi y over L. Well, phi sub I of y equals 0. Okay. But what about dpi dy? Okay, what y equals 0? What's that equal to? Well, I differentiate sine, I get cosine. And I said y equals 0 and it's cosine, I have cosine of 0 and it's not 0. It's something. Okay, so this is not 0. So I can't use those modes. Okay. All right. Now, when I take this equation, this representation, I'm only going to use one mode, right? I'm only going to use one mode. But we could use 2 modes, or 3 modes, or 4 modes. So let's do one. One at a time. I take this and put it in here. Then I use Galerkin's method. I can get this equation. Okay. What is Galerkin's method? I put this in here, and then I multiply by this mode shape, and I integrate from 0 to L. That's what. So this gives me an equation for H hat, which always depends on time now. I could have done something else. I could have taken this equation and put it up here, and perform these intervals. And once I perform these intervals, everything would appear in terms of H and H dot. And then I can use Lagrange's equations for H. Okay? Or, I could take this, put it in here, and write it all out, and then use Hamilton's principle, and also determine an equation for H hat. In this case, if I use these modes, I don't get the same answer in every case. So, what happened and why is that not? Why is that a problem? It's not a problem? You use different methods to get different answers? Close enough. But if you had to choose, which method would you choose and why? Actually, Fourier is the one that's likely to be wrong. Why? Well, because in Lagrange's method, there's no way of saying anything about the boundary conditions at the tip. Whereas in these other two methods, Lagrange's equations and Hamilton's principle take care of the so-called non-geometric boundary conditions, at least in an approximate way. And as the number of modes gets bigger and bigger, it does better and better in satisfying those boundary conditions. Whereas in Lagrange's method, there's no mechanism for doing that. However, if you only use a single mode, as we've done here, then you do get the same answer. So we are making an approximation here, not only just in terms of using one mode, but we're also probably not doing a very good job of satisfying the tip boundary condition. But as you suggested, maybe it's not too bad. Right? But the only way you would find out is to use more and more modes and see if the answer stops changing if you use enough modes. So this is something what I've just described as what I would do if I were in the very early stages of a new design, but this would be totally unacceptable if I were about to fly an airplane and I wanted to do a calculation. I want to compare my answer as computed with the flight test result, which is something you want to do eventually, right? There's a span of several years between the first calculation and the last calculation. Okay, so now some definitions. There's some coefficients here, and they involve these intervals. This physically is the total mass weighted by the mode shape, right? This is the mass per unit span, integrated over the span. So this would be the total mass of the wing, except there's a weighting factor because of these mode shapes that we use. So this is called the generalized mass. It's not the physical mass, but it's a mass associated with the mass distribution and the mode shape. This is the generalized stiffness, if you will. It also involves the mode shape. The interval of the mode shape square also appears, which we normalize usually by saying it's equal to the span of the wing, right? And we can normalize these modes any way we want to. This is a common way to do it. And then this is, if you will, a generalized gust velocity. It's the actual gust velocity weighted by the mode shape and then divided by L to make this have the same dimensions as the gust velocity. And if I use all these definitions, then I can simplify this equation to this form, which is a standard form. And what does this look like? This is a spring mass damper system. Here's the mass. Here's the spring. Here's the damping. The damping came from the lift, right? This is aerodynamic damping. And then this whole system, the spring mass damper system, is forced by a lift force associated with the guns. So you probably have seen this kind of equation in Professor Keel's course on vibration, except that he probably didn't talk about the damping coming from aerodynamics. This is, by the way, a fairly simple form of representation of a lift. We haven't talked about unfair aerodynamics and dispersion, but when we get to that in more depth, you'll see that it's sort of this way, but it's a little more elaborate. Okay? You still with me? So, all we have is a spring mass damper system with a forcing function into the gust. We want to find out how does this thing respond in time. We want to find out how does H change for time given a gust input. Cell phone, are you still happy over there? Right. Oh, they're not allowed. I'm sorry. They can't tell me.
The microphone working at all?
Nope. Sorry about that. I hope you're still with us. Now, let's go on. So we're going to solve that equation. And the way we're going to solve it is we're first of all going to assume a sinusoidal gust and a sinusoidal response. And we're going to use complex notation because it's compact, makes the algebra a lot easier. I mean, I could write this as a sine or a cosine, and trust me, this is easier. You have to accept the fact that this really is giving me the same answers I would get with sine and cosine, which is true. Okay. Then I can, once I assume sinusoidal motion, that differential function of time just becomes an Outbreak equation, right? Which depends on frequency because time has gone away. And therefore I can write the ratio of the amplitude of the response to the amplitude of the input. The amplitude of the bending of the wing to the amplitude of the gust. And I non-dimensionalize it because I like non-dimensionalization. So I'm non-dimensionalizing H bar by C, and I'm non-dimensionalizing the gust amplitude by the free stream velocity. And when I do that, that's what I get. This is the transfer function. And once I know the transfer function, it's almost all over in terms of computation. If I had 17 modes rather than one, I would not just have a transfer function. I would have a transfer function matrix, a 17 by 17 matrix, each element of which would look something like this. If I only have one mode, this is the whole thing. Now, from this example, we can see some interesting physical things without doing too much computation, numerical computation. First of all, we can look at what happens at resonance. At resonance, the inertia term and the stiffness term balance, right? The resonant frequency is when omega squared is equal to kh over m. So if that happens, notice everything sort of cancels out, and I find that the transfer function of resonance is a minus sign. Remember that minus sign that had to do with the lift is still there. Terrible thing. Dynamics doesn't ever do this thing. But that's not the important thing. The important thing is that the transfer function is just 1 over I. Well, I have to say what I means in this case. By the way, this I is square root of minus 1. Right? This is the imaginary. Look, it's just 1 over omega c over u. And that appears so often that we're going to give it a name. We're going to call it the reduced frequency, or the Struhel number or something. So this non-dimensional transfer function goes like 1 over the Struhel number. Notice the Struhel number gets small, this thing gets large. Struhel gets large, and this thing gets small. What's the I mean? It means that the response is 90 degrees out of phase with the input. Right? That's all. That's just telling me, that's talking about the phase shift at resonance. At resonance. Okay. More generally, we can work this out in a form that Aeroelasticity like. First of all, we can again define a natural frequency, which is kh over m. That's frequency squared, or you square root it, right? And then the general transfer function can be written in this form. Well, I've written this in the standard form associated with an damped spring mass oscillator because that's what dynamics is not allowed. But that means then I have to compute what this coefficient is by putting this term with this form. Right? That's what I've done here. And then I can solve this form for the damping coefficients. And it turns out it's equal to this. It involves another reduced frequency, but now it's the natural frequency. It involves the lift coefficient, which is a measure of how much aerodynamic force I have for a given motion. It involves mu, which is a mass ratio. This is rho of the fluid times the chord squared times the span divided by essentially the generalized mass, the structural mass of the wing. And in aeroelasticity, the fluid to structural mass ratio is really important. In turbine machinery, that number is typically so small that some approximations are made out here. We can't say, if we set mu to 0, we're going to throw away all the damping, right? We don't want to do that.
It changes if you're doing this stuff, so it's like liquid.
Oh, yeah, that's right. In water, this would be a much bigger number because rho would be a much bigger number. Yeah. So hydrofoils have one kind of mass ratio, and turbine machinery blades have another one. Okay. So with all that, we can write this transfer function in this form, which is a nice form for subsequent function. And we can also, having defined this transfer function, we can say that the response, the amplitude response, formula, is the transfer function times the amplitude it does. And if I believe in Fourier transforms, I can inverse Fourier transform this expression and find out how h is really h hat. H hat depends on time. For I, what is I? I'm glad you asked. I is the inverse Fourier transform of the transfer function. And by definition, it's this interval. It's the transfer function that depends on frequency multiplied by e to the plus I make d. You raise all frequencies, and there's a 2 pi. And I normally assign this as a homework problem, but in this case, I'm not going to the answer. If you work this out, I, this wonderful I, which depends on time, involves the dynamic pressure, the span of the wing, the lift curve slope, the mass of the wing, the natural frequency of the wing, the damping ratio of the wing, a damping ratio associated with air density, and then most importantly, E to some negative factor times a sine. So what is this physically? It's a damped oscillation. Right? This system is stable. It has positive aerodynamic damping. It doesn't flutter. This model doesn't flutter. Okay. So I fly through this wing, through this test, and I can determine how it responds. In time, or I can also represent it in terms of frequency. And that's that. Conversely, if I knew I to start with, I could compute the transfer function because it's Fourier transform. So we're done, right? Why? Because from this expression, I now know I know the dust time mystery. If I can perform this interval, I can determine the response. And I don't care what the dust response time mystery. It could be a random function of time, right? It could be any other function of time. This is it. This is the whole story. When I start out by simple sinusoidal motion of the dust and of the response, and then I go Fourier transform. That's all. Now, I'm going to stop here. The next thing we're going to do is we are going to talk more about the random test case, because it turns out one can do some very interesting things that have great computational results, physical advantages, and purposes of the result for the random input random case. Most people do not take this direction for a random input and find the mechanism. They do something else. Typically, what happens is even if I have a very random input, because of the resonant nature of the system, right, as a natural frequency, typically has fairly light damping. I have a very ragged-looking random input, but what comes out is something that looks pretty sinusoidal. There's a modulation of the amplitude because it is a random input, but it looks like it's multi sinusoid because that resonant frequency of the system acts as a filter and it filters out almost all the random inputs except for the frequency content of the dust, which is close to the natural frequency. And we want to take advantage of that. It's really hard to do. Let's stop now. Other questions? Other questions? Hearing none. Then you'll have to come back on Thursday for that. I'm going to quote some results from random analysis, which are described in gruesome detail in the book. So after I give you the big picture on Thursday, if you want to know how some of the results are obtained, you need to read the text. But I could write down all the equations in the text, but they're already there, and I can't explain any more simply. So please read the text on random inputs, outputs, if you really want to know a little bit more about the details. And we will see you then on Thursday. So, Colin, we miss you desperately in terms of your questions.